Monday morning. After 2 relaxing weekend days, what a better way to start a new week with an hour-long meeting, during which an old man is talking non-stop for 45 minutes. I can see some of you are nodding. I guess you all share my passion for Monday morning meetings. On Monday morning, to wake up your brain, we need to surprise it and entertain. If you care about children or FP, try not to fall asleep and bear with me. What have just happened? Your brains have noticed a pattern, a rhyme. It always pleases a brain to find a pattern. It pleases it even more if it finds an anomaly in a previously identified pattern. How do I know? Because I attended the Lambda Days conference in 2015, when a neuroscientist, Kinga Panasiewicz, gave a keynote on how computers change our brains. She spoke about cognitive and behavioral functions of a human brain. Her talk was such a blast that it was the first time in my life that after 1 hour of her lecture, I saw the audience asking her to keep going and skip the coffee break. Now you're thinking, oh, so this is where this is all going. He wants us to skip the coffee break. Kinga was a winner of the Road to Harvard competition. In 2014, she has been listed as one of 100 greatest Eastern European innovators. Her field of study was not directly related to functional programming, but the success of her talk and how the conference audience appreciated an interesting topic had an impact on all future editions of the conference. We continued to invite a keynote speaker who talked about topics other than FP, but still very relevant to our audience. My favorite quote from her talk, "Nice brain," is how you compliment a brain scientist. Her talk sparked my own interest in human brain and how we learn. Over the years, I collected a number of books on the topic. I have learned there are many types of memory: spatial memory, semantic memory. I visited museums of science where they have stations to run experiments and to make us experience how bias is present in our thinking or how memory is constructed. Lesson from 2015 edition: attending a conference can physically change your brain. So, how is the conference constructed? Does attending 1 year impact the following years? Each conference edition has a call for presentations, sometimes also a call for papers. Every year there's also a program committee which reviews submitted abstractions, and the committee can also invite speakers. I don't remember if in the following year Rob Martin has responded to our call for talks or someone invited him, but his talk of the 2016 edition about teaching functional programming to new developers was the most watched video in the history of Lambda Days, with 42,000 views. My favorite quote from that talk: "A language that fits together in as few abstractions as possible is easier to teach to new developers. If we start new developers with functional languages, we can get them thinking clearly from the start. They start off writing simple and correct code. You can watch the recording of his talk, but remember that a video once watched cannot be unwatched. Your brain will physically change. You have been warned. That year, there was a lot of interest in new functional languages. If we look at the last decade of functional languages, we notice that around 2014, quite a few new languages were released. The second most watched recording was the talk by Tomasz Kowal about Elm and Elixir, two functional languages created around 2012. Lesson from 2016 edition: keep an eye on emerging trends. Participating in a current debate is one of the factors contributing to a positive conference experience. Conferences are not only about the latest and greatest. Computing is a bit like the fashion industry. Some hot trends one year turn out not to be so relevant years later. On the other hand, some paper, initially not widely recognized, turns out to be very influential. One of such papers was titled "Why Functional Programming Matters" and was published by John Hughes in the 1990s. It is the most read paper by John. Him and Mary Sheeran jointly opened Lambda Days in 2017. If my memory serves me well, it was the most attended conference edition. John and Mary talked about the origins of functional programming and papers they found to be most interesting and influential during their careers. It was a wonderful review of the history. My favorite quote: "I don't need booleans if I have functions. What else don't we need? What about numbers? Who needs them?" Lesson from 2017: we are standing on the shoulders of giants. Not only listening to them, but also watching which talks they decide to attend during the event contributes to a positive conference experience. The following year, we were again lucky to have Philip Wadler appear on the stage for the second time. He spoke about the category theory and how mathematical abstractions can capture problems in computing in a very elegant way. He argued that the mathematical intuition, which we developed at school early in our lives, can be applied over and over again throughout our professional career. My favorite quote: "When you have a tough job to do, this is a job for mathematics. This is a job for lambda calculus." And then he transforms into a lambda man, a superhero whose superpower is maths and lambda calculus. Lesson from 2018: Philip Wadler is one of a kind. In the weeks after each conference edition, some of our attendees published blog posts describing what were the most influential talks from their point of view. It is fascinating to read how we choose which talk to attend, what we derive from the talk, how it sparks our future interests. I developed an interest in teaching. And over the years, the conference made me think a lot about learning. In 2020, we hosted Van Eindam, who shared her experiences in teaching. She even invited one of her secondary school students on this stage. And we had our youngest speaker presenting that year. Learning process is complex. There are no discrete states which one can put themselves into. Learning is messy, sometimes confusing. Children, while they grow, have an increasing ability to handle and manipulate information and think abstractly. Donald Clark said in one of his podcasts, cognitive mental model is like a washing machine. We are actively and proactively reorganizing, restructuring, resequencing all of our knowledge. Give people freedom and space to generate their own learnings. My favorite quote from Van Eindam, it's much easier to find a teacher to teach them how to code than to find a programmer and teach them how to teach. Oh, wait a minute. Let me try to challenge that. I started my teaching practice with children aged 6 and 7. Computers or tablets are not necessary when teaching children at this age. Actually, electronic devices are often a source of distraction, and they don't necessarily help. Children enjoy developing their social skills. Well, who doesn't? They start to relate themselves to their peers. A group of researchers from the University of Canterbury in New Zealand exploited it and created classes where children play active roles. Using movement when learning is a generative activity that helps to remember. The project is known as Computer Science Unplugged. It shows binary system, sorting, encoding, decoding, protocols, and many more computer science concepts. For example, one of the classes demonstrates how sorting network works. In this diagram, numbers which we want to sort are traveling from the right to the left. Each circle is an intersection of two paths where we need to compare two numbers. When two numbers meet in a circle, the lower number goes left, the higher number goes right. No matter in what order numbers start on the right, they always end up sorted on the left. Now, you may wonder, how can children play roles in this scenario? Here's how. We have four numbers on the right. From the top, these are 3, 4, 2, 1. The game goes on. At the end, we see sorted numbers from 1 to 4. For several years, I taught Computer Science Unplugged to 2 primary school classes. It was fascinating to see how children at the age 9 can develop a communication protocol with payloads split into several packets, packet ordering, lost packet detection, packet retransmission, all within 45 minutes, which is a single class in Polish schools. Feeling insecure about your job? I felt encouraged, even to the point where I started an after-school coding club and tried teaching programming to 10 and 11 years old. And then I started to struggle. Teaching 20 kids at once proved to be difficult. I subscribed to a program where I was learning how to run coding clubs and what to teach there. It was mostly Scratch and Python. We had also robots. It all seemed like a good idea, but I struggled. So I continued my quest to find and try effective teaching methods. I came across the Bootstrap project, created by researchers at the Brown University in the United States. Katy Fissler, one of the Bootstrap project leaders, presented at Lambda Days in 2021. The Bootstrap project uses functional programming to teach subjects such as algebra, data science, and physics. They developed a very rigorous and engaging content. They approach it with a truly scientific spirit. Their content was evaluated with scientific methods, and they published a lot of academic papers. My favorite quote from that presentation: when we take ideas that we use in functional programming and stage them aligned with what the teachers are already teaching, we get a powerful combination. It was a great inspiration for me. In Polish schools, on the subject of mathematics, students learn about numbers, algebra, sets, functions, geometry, probability, logic, and a few other topics. And inspired by the Bootstrap project, we started to think about ways to exploit what students already know and what they intuitively understand. I wanted to understand what did we teach in math classes in the past and what do we teach today. I visited an old bookstore and found an algebra textbook. Textbook by Andrei Kisielov. He was a Russian math teacher born in the 19th century. He wrote very popular textbooks, which were in use until 1950s. They were in regular use for over 60 years. Very good textbooks. I studied how he introduces arithmetic operations, algebraic expressions, and how he provides historical context of mathematical notion conventions. These notions have changed over the centuries, but not so much in the last 100 years. Today, we are hosted by the Jagiellonian University in Auditorium Maximum. Not far away from where we are now, there is Collegium Novum of Jagiellonian University. And a few-minute walk from there, we can find a sculpture of Professor Stefan Banach, very famous mathematician known for functional analysis and Banach space. Sound doesn't work, but Banach in 1930s wrote a series of textbooks which were in use for many years in Polish schools. Let's see how he defines a function. He starts with a definition of a square and how to calculate area of a square. He then notes down an algebraic expression to represent a formula for calculating square area. And from there, he derives a function defined with the very formula. Not too formal, but easy to follow, and gives us some intuition on what a function is. In modern Polish textbooks, we use the same conventions. We provide many examples of expressions and start practicing them at the age of 10 or 11. In my teaching practice, I try to translate examples from the math textbooks into Elixir Live book notebooks. Elixir is a functional programming language. Livebook is a web-based tool for coding and collaboration. It is somewhat similar to Jupyter Notebook, but it is designed to serve a functional language. I found Livebook to be a very high-quality project. It allows students to collaborate on the same coding notebook. When students can translate examples from the textbook into interactive code cells, it is a very engaging experience. For example, in the textbook, they ask to note down algebraic expressions representing formulas of perimeters. We can then take the algebraic expression and use it to define a perimeter function. The same way as Professor Stefan Banach did in his textbooks. We can then apply the function and immediately see the computed result. This immediate effect of our work visible on the screen is crucial in the process of learning. My students enjoyed it very much. Modern textbooks introduce interesting algebraic patterns. Let's take this composition as an example. The textbook reads, think about a number multiplied by 5, then subtract 5, then subtract 3 times the original number, then add 15. So if the result is 18, what was the original number? In Elixir, we can note it down with function composition, which uses the arrow notation, pipe and greater than bracket. The code notation is not far from the textbook notation. What they already learn at school helps during the coding club classes. They also can see why they have to learn the math concepts in the first place. We demonstrate how math is used in computing, how they can use what they learn in schools to design computations. They become programmers of computers. When mapping math concepts to computing, the functional paradigm is very handy because its foundations are built on mathematics. At schools, we already teach a lot of patterns that are close to functional programming. We teach substituting a value into a variable and then evaluating an expression. We teach definitions of geometric functions like area of a square or perimeter of a triangle. We teach set theory, which is not far from data structures. We can also teach other programming concepts like recursive function or pattern matching. I have one more inspiration to share. Last year, Sam Aaron gave a talk on the Sonic Pi project. It is an open source music creation and performance tool. It was initially developed as a postdoc research project to help introduce and teach programming concepts in schools, but has since grown into a powerful musical instrument. In the talk, he examines how functional programming techniques have both been a major influence and are a critical part of the future of the project, from its roots in Clojure to its future on the beam. My favorite quote from the talk: programming not a tool for business, but a tool for human expression. Two years ago, I stepped down from chairing the program committee of Lambda Days to focus on teaching. Together with my wife, Anya, we started to develop lesson scenarios where we teach computer science concepts like recursion. Recursion is an important concept both in maths and in functional programming. How to explain recursion in an engaging way? Trees grow in patterns. In maths, a fractal is defined using recursion. We can grow a fractal tree. This kitty, named Jovita after the first Polish female programmer, is growing a fractal tree in the picture. We used a simple recursive algorithm to generate trees. And students could experiment on their own with the number of iteration, randomness, and other parameters, which would result in quite realistic trees, similar to those created by Mother Nature. We then used an artistic technique of press printing to transfer the fractal tree to a backpack so that girls could take them back home with them. Our hope is that by showing patterns, doing things, and building on top of their intuition, we can keep them engaged. In long-term learning requires an intrinsic motivation. In our classes, we are trying to identify what sparks an intrinsic motivation. Another example, how to make children familiar with code editing, compilation, debugging, conditional statement. We tried Ink programming language, which compiles to interactive books and is used to develop narrative games. Our class created characters, then a story and a storyboard, which allowed us to capture how the story narrative can branch off. The Ink programming language compiles to an interactive book where the reader decides which branch the story to take and how the story develops. The end result of making was published online, and girls could show their book to parents, relatives, or peers, and this kept them motivated. I have shown you one of many paths that people could experience the Lambda Days conference over the last 9 years. Today we start the 10th edition of the conference. What will inspire you over the next 2 days? Thank you.
Okay, we still have some time for Q&A. So, questions. If you have questions, raise your hand and I will bring you the microphone.
Hello, thank you for the talk. It was super fascinating and inspiring. I was wondering, it's very interesting how you find new ways of, making things more pedagogical. Do you have any plan to translate those things from the classroom to the industry in general, or just, to make more interesting tools for the future of programming?
Can you repeat the question again slowly? Sorry.
Yeah. Do you think you could translate what you learn in the classroom, like all those tools that you're making, to the industry in general, like what would making new tools for programming?
This hearing here is very bad. And can you repeat the question, Jan?
Yes. Can you translate the lessons you learned from teaching kids to some tools that can be used in the industry?
Thank you very much. I'm sorry I didn't hear the question.
Yeah, we just need to speak slower because there's some echo in the room, and that's it.
Brain of a child is not different from a brain of an adult. The learning techniques that work at school work in our adult ages as well. I think the most interesting part of the school classes I've been running was this immediate effect, when you can try something and at this very moment see what is the result, what is the effect of what you just tried, so that you can then manipulate, change, and continue exploring. And I think this is also applicable in a professional environment. Interactive notebooks like Livebook or Jupyter or Google Colab, those are examples of such tooling. And they are nowadays widely adopted to introduce new people into a project. When you onboard new developers, they are also used to document existing systems, to demonstrate how they work. So I think this would be my takeaway. This short, immediate feedback loop is very good for teaching.
Any more questions?
Let's try whether you understand this. So you presented these boxes in which you start with an X and then you multiply by 5 and etc. And you showed us how you implemented in Elixir. Quite nice, extreme. But you asked the question in the talk here, okay, but if I get the answer 18, what X should I have used? So is that something the kids are going to explore and write this inverse sequence? Or is that something your tooling would offer them? Or what would be the next step in that? Because one thing is to write down that algorithm that gives you the answer. The other thing is to think about, how did I get to the origin if I have the answer?
So I think there are two aspects here. One, there is this immediate question to be answered. If the result was 18, what was the original number? And every child may have a different way to find the solution to the question. They could experiment with the live book by changing the original number until the result is 18. They could do it on a paper. So this is always very individual, how they go about solving a problem. And this is one part. The other part is that while you try solve, you're learning a concept, a pattern. So what I'm interested in is when they explore solutions and the problem, they actually get to experiment with this function composition. We don't necessarily need to explain this is a function composition. We just need to try and see what changing the order would do, or what changing the original value would do, and so on and so on. Just so that later, when we apply it in a different context, they have some intuition, they have something to relate to. As the memory is constructed in an associative way, we associate one fact with another. My hope here is that they get to experience this solution so that later they can start to recall it in another problem space. So it's more about experimentations.
Well, I will be a bit skeptical because, yeah, tooling, you're right. Tooling is important, but I have kids and I try them to teach some mathematical concepts. And biggest problem is repetitivity. From beginning, it's fun and interesting, but later they better spend time playing Nintendo than doing things you think. And their surroundings, their friends, also not so interested in mathematics. So maybe you have a recipe for this problem.
Can you please repeat the question slowly? I'm sorry, but the feedback is...
What to do with kids surrounding friends if they not interested in topic in mathematics? Because I think it's more important than tooling.
Okay. So let me repeat the question to make sure that I understood. What if your peers, colleagues in a classroom are not interested in maths? How to spark this intrinsic motivation? Recently, I've been exactly thinking about it because after a few weeks of running the class, I saw that the class was less and less and less engaged. So I first tried to impose some projects on them. Let's build something complex but very cool. And then they disengaged even more. So I had to find something which they can do, they can run, they can push moving forward. We came up with an idea that they will design like an escape room for school. Like there is a game, Paper Chase, where one team is going some path and leaving some riddles and clues behind them. Second team is following the riddles, following the first team. It's called Paper Chase. So we used this idea to design a school paper chase game with stations being implemented in a functional language, with live books deployed online. So children now can go and scan some QR codes or solve puzzles online. And believe me that all people involved in creating the game, when they knew that others will be playing the game later, they had a lot of joy and they were very engaged. So the social context is very useful to motivate. Even if you are not into maths, but you are part of some social activity, it might be strong enough intrinsic motivation to explore some ideas. Actually, one of my students who dropped out from the class, when she heard about this game design, she rejoined because she didn't want to touch math, but she wanted to be involved in creating riddles.
More questions?
Hi. From teacher perspective, what's more important for kids? To give them an intuition how something works, or to give them a hard knowledge how something works?
Give them space to explore some problem. You may spark their interest with the initial problem statement, but then give them space to explore on their own. Like, how did you learn when your parents told you not to do something? Did you follow? Or did you have to try yourself first to derive your knowledge, your learning from it. I think that's the mechanism here. You need to give them space and opportunity to try things out, but we as teachers can set the stage, give the initial ignition.
Questions?
Hello. It sounds very great to give kids open space and treat them as a person who can make something new and interesting. But in the end, on the exam, we will meet the old paper book. The old paper book with old tests. So what educational system can it accept your new steps toward a new direction? Is it possible to have this in official school, official exams, for example? Because this system is quite strong. It didn't change for decades, you know.
So again, what is the question? Can you please repeat?
The question, can Poland, for example, educational system accept your investigations, for example? I don't know if investigations or not.
So classes, national curriculum, they have certain rigor, so that over years of school we can evaluate some progress. And this progress is evaluated through some methods and testing, and this is how it is. It's not only Poland, it's most countries, how they evaluate progress over the years. So that's on one side. How do we fulfill the obligations to the national curriculum? The other one is that nowadays trying to make children focus on something, their attention span is very narrow. It's not easy to let them just read a textbook and solve all those equations one after another. So what I'm proposing here, or exploring here, is can we find some alternative methods to help teachers teach the national curriculum as they used to, with additional tooling, concepts, practices. I am currently collaborating with some group of teachers and trying to get inspiration from them, but also inspire those teachers to try our lessons. The lessons we have developed were run outside of school, after school classes. I did not have a chance to teach in this very way at the school environment yet. But I hope for some collaboration with the teachers and the educational system of Poland in the following years.
Questions?
Okay, so hi. First of all, great presentation. My question is about the fact, because you told about this loop of instant feedback. And my question is, don't you think it might be addictive for young children to show them the results right away? Because it's great for some easy problems, but sometimes we have more complex problems, and this child might be bored by the fact that he needs to spend more time on doing it. Don't you think that it might be like dangerous?
Again, I think it all boils down to intrinsic motivation. If at the age of 10, 11, 12, maybe a little bit older as well, you can spark this intrinsic motivation that they will find it useful, funny, interesting, they will go the extra mile. But how not to put them off in the first place? That's the big question. So although I agree some of the examples here are simplistic, they don't explore in depth the complexity of the topic, that was not my goal. I don't want computer scientists at the age of 10, but I want them to stay on the path towards becoming STEM, scientists one day.
Thank you for the talk. The question is, are you targeting the girls in particular in your teaching?
So my current class consists of girls only, yes. I tried teaching boys and girls. This was the class of 20 I mentioned during the presentation. And nowadays I focus on girls only, yes.
Hi, thank you. You show us a good example of how to teach maths and programming languages to kids. But what do you think that are the errors that we are doing and we should stop do?
So evaluation is a great way to improve. We should keep evaluating. I will give you one example. England, in the United Kingdom, they were the first country to introduce computing as an obligatory new subject in primary school. From the first grade in England, they teach computing. Almost 10 years later, when you look at the demographics of mathematics, the subject which at certain stage of English education, children decide which subject they want to study, so they choose which subjects they want to continue with. If you look at the mathematics, 50-50 is the split between boys and girls. Computing, this new subject introduced in 2014, has a split of 80% boys, 20% girls. So this is like a reference for me. There's something happening somewhere which makes those numbers as we see them. I don't have good answers what exactly we do wrong or what to do to make it different, but this is exactly the hot topic I'm trying to explore by trying different methods, scenarios, setups. So I would love to answer your question in a few years' time. I think this topic is actually a hot topic globally. Many countries started to follow this suite and they introduced obligatory computing in primary schools, and everyone is exploring different methods and what makes it an effective pedagogy. So it's a cutting-edge research, I would say.
Hi, thank you. So you just answered the other question that you initially had mixed groups of boys and girls, and now just girls. So why did you switch to just teaching girls?
The numbers I just quoted is one of the reasons. What makes children drop out from this computing path or STEM subjects in general? I don't know fully, but I'm trying to focus on this group to find out more about their intrinsic motivations, what would make them motivated for a long time, what would make them stay in this area. Because at the age of 10 and 11, both boys and girls demonstrated similar engagement. They were equally participating, and it was all equal. There was no difference. But yet, 3-4 years later, we see those numbers dramatically change. So this was one of the motivations for me to try to focus on this group and see if I can help.
Great, thank you.
Okay, do we have more questions? Okay, and on my way there, maybe my question. What do you think is the optimal room size for teaching computing?
Hard question. I tried the classes which are as small as 2, 3 in a small meeting room, and it works very nice because it's easy to communicate, they feel very safe. I can pay attention to every single question. I tried those big classes, 20 plus, and I just couldn't follow all the questions, and students were frustrated that they want to ask a question and they have to wait 5, 10 minutes for me to actually pay attention. So I would say try some group and see how it works for you. I don't have an optimal number, but the smaller the group, the easier it gets.
Okay, thank you. Next question.
Thank you for the talk. So you have shown your methodology of teaching kids, right? And there was also an example of teaching kids sorting algorithms, right? So where the kids were like hoping and you know. So the question is this methodology actually effective, and how it compares with the standard methodology of teaching?
So Computer Science Unplugged project has been running for almost 30 years now. It has been adopted in different languages, translated to different languages. I didn't follow the exact history of the project, if anyone has ever measured the effectiveness of the method. But again, at this age, my hope is that we give them an opportunity to see some patterns, get some inspiration. It's not necessarily to rigorously teach them how TCP/IP works. If they can think about the problem space and come up with some rules which turn out to be not far from TCP/IP design, that's for the better. But not necessarily we want them to name the protocol as such. So what I'm trying to say is that in this 6, 7, until 10 years old, I'm more interested in inspiring, hoping that sometime in the future they will reflect on what they have seen in the past. Some of the girls in my current class who are 12 years old, they used to also participate in those Computer Science Unplugged classes. When we do some live coding, they recall, oh, isn't it this binary notation that we used? Oh, isn't it this fax machine scenario that we tried? So 5 years later, at the age of 12, they recall what we discussed at the age of 7. And I think this is maybe not a scientific proof, but it's some evidence that we learn by doing, and when we construct our knowledge through associations.
Why functional programming? Because I think the most common options are Java, C, Python to introduce kids into programming.
I have no problem teaching other languages. However, imperative languages were modeled after how CPU works, how machine works. The abstractions present in some of those languages, they mimic the actual machine underneath running the computations. So to introduce a child to an imperative language, we need to first introduce some new concepts and abstractions which are derived from how machine works. With functional programming, there is no need for such. We can keep exploring the space of math problems, math notation. This is not far from functional programming paradigm. I find it easier to use the notation which is so close to the school textbook. and I found it harder to explain why we need some extra syntax, extra syntactic sugar to combine some concepts. I'm just one of many exploring this space, so others may have other opinions, but this is my answer to the question. Notation, being close to the notation they are familiar with.
Okay, questions? Okay, I have last question, maybe. So we were talking about the size of the room, so the smaller the better. And these days we observe some improvements in AI technology. And I don't know if you followed what is happening on Khan Academy website. So they're introducing this personalized AI teaching assistant. So the question is, do you think is this something that we already can try to adopt in modern classrooms? Or is it still missing the human touch? Is it too text-based still? Or can we already use it efficiently?
So as far as I've seen, Khan Academy published some videos. So it was like a closed beta testers that have access to their new technology. I would definitely want to try it out when it becomes publicly available. I think it might be very interesting to be able to personalize your learning path. This is what the teacher does in a smaller group. He or she can navigate individual learning paths. A teacher cannot do it in a group of 20 if AI aid classes would help us find what are the gaps and how to navigate this individual learning path. Maybe that's the future. I don't want to make any claims here yet, but I will give it a try.
Okay, so let's give a warm round of applause to Michał.